What if everything you see around you, the stars, the planets, even the air you breathe, was once compressed into a single point smaller than an atom? This isn't science fiction. It's the story of the Big Bang, the moment our universe burst into existence over 13.8 billion years ago. But here's the twist: the Big Bang wasn't just an explosion. It was the beginning of a cosmic dance that continues to unfold, revealing secrets about the very fabric of reality. In this video, we'll take you on a journey through 25 incredible discoveries about the Big Bang and cosmic inflation. Discoveries that have reshaped how we understand the universe. From the faint afterglow of the Big Bang to the mysterious force of dark energy, each revelation brings us closer to answering the ultimate question: how did it all begin? Stay with us, because by the end of this video, you'll see the cosmos in a whole new light. Ready to explore the origins of everything? Let's dive in. Now, turning to the first of our 25 discoveries, we explore the cosmic microwave background, or CMB, often referred to as the afterglow of the Big Bang. This faint radiation fills the entire universe, and its discovery in 1965 by Arno Penzias and Robert Wilson was nothing short of accidental. While working with a sensitive radio antenna, they detected a persistent noise that seemed to come from all directions. At first, they thought it might be interference from pigeon droppings on their equipment, but after thorough cleaning and testing, the signal remained. What they had stumbled upon was the oldest light in the universe, a relic from a time when the cosmos was just a hot, dense soup of particles. This discovery was monumental because it provided the first direct evidence for the Big Bang theory. The CMB is like a snapshot of the universe when it was only 380,000 years old, capturing the moment when atoms first formed and light could travel freely. By studying its subtle variations, scientists have been able to map the early universe, revealing the seeds of galaxies and large-scale structures we see today. The CMB is often called the smoking gun of the Big Bang because it confirms that the universe was once incredibly hot and dense and has been expanding ever since. This discovery not only validated the Big Bang theory, but also opened the door to understanding the universe's infancy in unprecedented detail. As we move forward, this ancient light continues to guide us, offering clues about the origins of everything we know. Now, shifting our gaze to the next monumental discovery, we delve into the work of Edwin Hubble and his groundbreaking revelation that the universe is expanding. In the 1920s, Hubble made a startling observation while studying distant galaxies. They were all moving away from us, and the farther away they were, the faster they seemed to be receding. This phenomenon, now known as Hubble's law, was a game-changer for cosmology. It provided the first observational evidence that the universe wasn't static but was instead growing larger over time. Hubble's discovery was rooted in the concept of redshift, a key piece of the puzzle. When light from distant galaxies travels through the expanding universe, its wavelengths stretch, shifting toward the red end of the spectrum. This redshift is like a cosmic fingerprint, revealing how fast a galaxy is moving away from us. Hubble's measurements showed a clear pattern: galaxies were racing away in all directions, as if the fabric of space itself was stretching. This observation became a cornerstone of the Big Bang theory, suggesting that if the universe is expanding now, it must have been smaller and denser in the past. Edwin Hubble's contributions didn't just stop at proving the universe's expansion. His work laid the foundation for modern cosmology, transforming our understanding of the cosmos. By establishing a relationship between a galaxy's distance and its velocity, Hubble provided a way to measure the scale of the universe. His discoveries also paved the way for later breakthroughs, such as the identification of dark energy and the precise calculation of the universe's age. Hubble's legacy is a testament to the power of observation and curiosity. His findings not only confirmed that the universe had a beginning, but also opened the door to exploring its ultimate fate. As we continue our journey through these incredible discoveries, Hubble's work reminds us that the cosmos is a dynamic, ever-changing tapestry, full of mysteries waiting to be unraveled. Now turning to the next chapter in our cosmic journey, we explore one of the most compelling pieces of evidence for the Big Bang, primordial nucleosynthesis. This process, which unfolded in the first few minutes after the universe's birth, explains how the lightest elements in the cosmos came into existence. Imagine the universe as a seething cauldron of energy, so hot and dense that even atoms couldn't form. As the universe expanded and cooled, conditions became just right for the first nuclei to emerge. During this brief window, protons and neutrons combined to form the simplest atomic nuclei: hydrogen, helium, and a trace amount of lithium. This process, known as nucleosynthesis, was like a cosmic recipe, with the exact proportions of these elements determined by the universe's temperature and density at the time. The Big Bang theory predicts that about 75% of the universe's ordinary matter should be hydrogen, 25% helium, and a tiny fraction lithium. Remarkably, when scientists measure the abundances of these elements in the oldest regions of the universe, they find a near-perfect match to these predictions. This agreement between theory and observation is a triumph for cosmology. It not only supports the Big Bang model, but also gives us a snapshot of the universe's earliest moments. The fact that we can calculate the exact amounts of these elements and find them reflected in the cosmos today is a testament to the power of science to uncover the secrets of our origins. As we continue to probe the universe's history, primordial nucleosynthesis stands as a cornerstone, reminding us that even the simplest elements carry the story of the cosmos within them. Now stepping into the realm of cosmic geometry, we encounter one of the most puzzling questions in cosmology, the flatness problem. This mystery revolves around the universe's remarkable balance. Why does it appear so finely tuned between expanding forever and collapsing back on itself? To understand this, picture the universe as a vast cosmic sheet. If this sheet were too curved, the universe would have collapsed long ago under its own gravity. If it were too open, galaxies and stars would never have formed. Yet, observations show that the universe is almost perfectly flat, a delicate equilibrium that defies explanation without invoking something extraordinary. This is where cosmic inflation comes to the rescue. According to this theory, in the first fraction of a second after the Big Bang, the universe underwent an exponential expansion, stretching space itself to an unimaginable degree. This rapid stretching smoothed out any curvature, much like blowing up a balloon makes its surface appear flatter. Inflation doesn't just explain why the universe is flat, it predicts it. The theory suggests that the universe's flatness is a natural consequence of this early, rapid expansion, solving the flatness problem in one elegant stroke. But why does this matter? The flatness of the universe isn't just a curious detail, it's a cornerstone of our understanding of cosmic geometry. It tells us about the universe's overall shape, its density, and even its ultimate fate. Without inflation, the universe's flatness would remain a baffling coincidence. With it, we gain a deeper insight into the forces that shape the cosmos and continue to guide its evolution. As we peel back the layers of this cosmic mystery, the flatness problem stands as a testament to the power of inflation to illuminate the universe's deepest secrets. Now shifting our gaze to another cosmic puzzle, we encounter the horizon problem, a question that has long baffled scientists. Imagine looking at two distant regions of the universe, so far apart that light from one could never have reached the other. Yet, these regions share the same temperature as if they were once in perfect thermal equilibrium. How is this possible? Without some mechanism to explain this uniformity, the universe's temperature balance seems almost miraculous. This is where cosmic inflation steps in with a groundbreaking solution. In the earliest moments of the universe, inflation proposes that space expanded faster than the speed of light, stretching regions that were once in close contact far apart. This rapid expansion smoothed out temperature differences, ensuring that even distant regions of the universe ended up with the same temperature. Think of it like stretching a piece of dough. Any irregularities or hotspots are smoothed out as the dough expands. Inflation doesn't just explain the horizon problem, it predicts the uniformity we observe, providing a natural and elegant solution to what would otherwise be a profound mystery. But why does this matter? The horizon problem isn't just a curiosity, it's a critical piece of evidence supporting the theory of cosmic inflation. By solving this puzzle, inflation strengthens its case as the leading explanation for the universe's early moments. It also gives us a deeper understanding of how the universe evolved from a hot, dense state into the vast, structured cosmos we see today. As we unravel the implications of the horizon problem, we gain not only insight into the universe's past, but also a clearer picture of the forces that continue to shape its destiny. Now turning to the microscopic origins of the cosmos, we delve into the fascinating world of quantum fluctuations, the tiny ripples of energy that set the stage for everything we see today. In the earliest moments of the universe, even before the first stars or galaxies formed, the fabric of space was alive with these minuscule, random variations in energy. These fluctuations, born from the quantum realm, were so small that they might seem insignificant at first glance. But when cosmic inflation kicked in, stretching the universe exponentially, these tiny ripples were magnified into the seeds of cosmic structure. Imagine throwing a handful of pebbles into a calm pond. The ripples spread out, creating patterns on the water's surface. In a similar way, quantum fluctuations were stretched by inflation, leaving behind a faint imprint on the universe. This imprint is what we now observe in the cosmic microwave background, or CMB, the afterglow of the Big Bang. The CMB is like a snapshot of the universe's infancy, and within it we can see the faint traces of those early quantum ripples. These patterns are not random, they are the blueprints for the galaxies, clusters, and vast cosmic webs that fill our universe today. But why are these fluctuations so important? Without them, the universe would be a featureless void, devoid of the structures that make it so rich and dynamic. These tiny seeds grew over billions of years, pulled together by gravity to form stars, galaxies, and everything in between. They are the reason we have a universe filled with complexity and beauty, rather than a uniform sea of particles. By studying these fluctuations, scientists can trace the universe's evolution from its earliest moments to the present day, unlocking clues about how it all began and how it continues to grow. As we explore these quantum seeds, we gain a deeper appreciation for the delicate balance that shaped our cosmos. They remind us that even the smallest things can have the most profound impact, setting the stage for the grand story of the universe. And with that, we move closer to understanding not just where we came from, but how the intricate tapestry of the cosmos was woven together. Now shifting our gaze to one of the most profound mysteries of the cosmos, we encounter the enigmatic force known as dark energy. This invisible energy, which permeates all of space, is not only driving the universe's expansion but causing it to accelerate, a discovery that has reshaped our understanding of the cosmos. In the late 1990s, astronomers made a startling observation while studying distant supernovae, the explosive deaths of massive stars. These supernovae, which serve as cosmic mile markers, appeared dimmer than expected, suggesting they were farther away than previously thought. This unexpected dimness revealed a shocking truth. The universe wasn't just expanding, it was speeding up. The implications of this discovery are staggering. For decades, scientists believed that the universe's expansion, set in motion by the Big Bang, would gradually slow down due to the pull of gravity. But dark energy, acting as a kind of cosmic repulsive force, is counteracting gravity's grip, pushing galaxies apart at an ever-increasing rate. This revelation not only earned the researchers the Nobel Prize in Physics, but also opened a new chapter in cosmology, forcing us to rethink the universe's ultimate fate. But what exactly is dark energy? While its true nature remains one of the greatest unsolved puzzles in science, it's thought to be a property of space itself, often associated with Einstein's cosmological constant, a term he once called his greatest blunder. Yet this blunder might hold the key to understanding why the universe is expanding faster and faster. Dark energy makes up about 68% of the universe's total energy content, dwarfing the contributions of both ordinary matter and dark matter. Its dominance suggests that the universe's future may be one of endless expansion, leading to a cold, dark, and increasingly isolated cosmos, a scenario often called the Big Freeze. This discovery also has profound ties to cosmic inflation. Just as inflation caused the universe to expand exponentially in its earliest moments, dark energy seems to be driving a similar, though slower, acceleration today. Some theories even suggest that dark energy could be a remnant of the inflationary epoch, a lingering echo of the universe's explosive birth. By studying dark energy, we're not only uncovering clues about the universe's fate, but also gaining insights into its origins. As we grapple with the mysteries of dark energy, we're reminded of how much remains unknown. It challenges our understanding of physics, pushing us to explore new ideas and theories. And while its true nature eludes us, one thing is certain: dark energy is shaping the destiny of the universe, and with it, our place within the cosmos. Now, stepping back to the very beginning, we arrive at one of the most transformative ideas in cosmology, the inflationary epoch. Imagine the universe in its earliest moments, a fraction of a second old, smaller than an atom, and filled with unimaginable energy. In this fleeting instant, something extraordinary happened, a rapid, exponential expansion that stretched the fabric of space itself faster than the speed of light. This is cosmic inflation, a theory that has revolutionized our understanding of the universe's birth and its subsequent evolution. But why is inflation so crucial? For starters, it solves some of the most puzzling questions in cosmology. Take the flatness problem, for example. The universe appears remarkably flat on large scales, a delicate balance that seems too perfect to be a coincidence. Inflation explains this by stretching space so dramatically that any initial curvature is smoothed out, leaving the universe nearly flat. Then there's the horizon problem. Distant regions of the universe, which should never have been in contact, share the same temperature and properties. Inflation solves this by proposing that these regions were once close together, sharing thermal equilibrium before being rapidly driven apart. The evidence for inflation is compelling, though indirect. One of the strongest pieces comes from the cosmic microwave background, the afterglow of the Big Bang. Tiny fluctuations in this ancient light reveal the seeds of structure in the universe, clumps of matter that would eventually grow into galaxies and galaxy clusters. These fluctuations match the predictions of inflation, suggesting that quantum fluctuations in the early universe were stretched to cosmic scales during this rapid expansion. Additionally, the uniformity of the cosmic microwave background across the sky supports the idea that inflation once smoothed out the universe. Inflation also ties into the broader story of the Big Bang. It doesn't replace the Big Bang, but rather enhances it, explaining how the universe transitioned from a hot, dense state to the vast, structured cosmos we see today. Without inflation, many of the universe's features, its flatness, its uniformity, and its large-scale structure would remain mysteries. It's no wonder that inflation is considered a cornerstone of modern cosmology, a theory that has reshaped our understanding of the universe's origins. Yet, as with any groundbreaking idea, questions remain. What triggered inflation? What brought it to an end? And could there be evidence beyond the cosmic microwave background that confirms it? These are the challenges that drive cosmologists forward, pushing the boundaries of our knowledge. As we continue to explore the inflationary epoch, we're not just uncovering the universe's past, we're glimpsing the very mechanisms that shaped everything we see today. Now, shifting our focus to another groundbreaking frontier in cosmology, we delve into the search for primordial gravitational waves. These ripples in space-time, born during the inflationary epoch, are like faint echoes from the universe's earliest moments. If detected, they would offer direct evidence for cosmic inflation, providing a window into the universe's explosive birth. Gravitational waves are distortions in the fabric of space-time, predicted by Einstein's theory of general relativity. While we've detected gravitational waves from cataclysmic events like black hole mergers, primordial gravitational waves are far more elusive. They originate from the rapid expansion of the universe during inflation, when quantum fluctuations were stretched to cosmic scales. Detecting these waves would be like finding a fingerprint of inflation itself, confirming not just that it happened, but how it happened. However, finding these ancient ripples is no easy task. They are incredibly faint, buried beneath layers of cosmic noise. One of the most ambitious efforts to detect them was the BICEP 2 experiment, which aimed to find their imprint in the cosmic microwave background. In 2014, the team announced a potential discovery, sparking excitement across the scientific community. The signal they detected, known as B-mode polarization, seemed to match predictions for primordial gravitational waves. But further analysis revealed that the signal could have been caused by interstellar dust, casting doubt on the findings. This controversy highlighted the immense challenges of this search, but it also underscored its importance. The quest for primordial gravitational waves continues, with experiments like the Simons Observatory and future space missions like LightBird refining their techniques. These efforts aim to distinguish between the faint signals of inflation and the cosmic dust that obscures them. Success would not only confirm inflation, but also shed light on the energy scales at which it occurred, offering clues about the fundamental forces that shape the universe. As we push the boundaries of our technology and understanding, the search for primordial gravitational waves reminds us of the profound mysteries that still surround the universe's origins. Each step forward brings us closer to unraveling the story of cosmic inflation, and with it, the very fabric of reality itself. Now, turning to one of the most mind-bending ideas in modern cosmology, we explore the multiverse hypothesis. This concept suggests that cosmic inflation didn't just create our universe, it might have spawned countless others, each with its own unique set of physical laws and properties. Imagine a vast cosmic landscape where universes bubble up like foam in an endless sea, each one a separate reality. This idea emerges from the theory of eternal inflation, which proposes that once inflation starts, it never truly stops. Instead, it continues in some regions while slowing down in others, creating pockets where new universes can form. The multiverse hypothesis challenges our understanding of reality itself. If true, it means our universe is just one of many, each potentially governed by different rules. Some might have stronger gravity, others might lack dark energy, and some could even have entirely new forces we've never imagined. This raises profound questions. Why does our universe have the specific laws and constants that allow life to exist? Is it just a lucky coincidence, or is there a deeper reason? These questions lie at the heart of the multiverse debate, sparking intense discussions among scientists and philosophers alike. However, the multiverse hypothesis is not without its critics. One major challenge is that it's incredibly difficult to test. Since other universes would be beyond our observable horizon, we can't directly observe them. Some argue that this makes the multiverse more of a philosophical idea than a scientific one. Others counter that indirect evidence, such as anomalies in the cosmic microwave background or unexpected patterns in particle physics, could hint at the existence of other universes. The debate continues with no clear consensus in sight. Despite the uncertainties, the multiverse hypothesis has profound implications for our understanding of the cosmos. It suggests that the universe we see might be just a tiny fraction of a much larger, more complex reality. This idea pushes the boundaries of science, forcing us to rethink what we know about existence, causality, and the nature of reality itself. As we continue to explore the mysteries of cosmic inflation, the multiverse remains one of the most fascinating and controversial ideas in modern cosmology. Now, shifting our focus to the very beginning of everything, we arrive at the Big Bang singularity. This is the moment when all matter, energy, space, and time were compressed into an infinitely dense and hot point. It's the starting point of our universe, the spark that ignited the cosmos as we know it. But here's the catch: according to our current understanding of physics, this singularity is where the rules of general relativity, Einstein's theory of gravity, completely break down. At such extreme conditions, the equations that describe how gravity works simply stop making sense, leaving us with a profound mystery. The singularity represents a boundary beyond which our knowledge falters. It's a place where the density and temperature are so extreme that the very fabric of space-time becomes unpredictable. Physicists believe that to truly understand what happened at the Big Bang singularity, we need a new framework, one that combines general relativity with quantum mechanics. This is where quantum gravity theories come into play. These theories aim to describe how gravity behaves at the smallest scales, where particles and forces interact in ways that defy our everyday intuition. One of the leading candidates for such a theory is string theory, which suggests that the fundamental building blocks of the universe are not particles but tiny, vibrating strings. Another approach is loop quantum gravity, which proposes that space-time itself is made up of discrete, quantized loops. Both theories attempt to bridge the gap between the very large and the very small, offering potential insights into the nature of the singularity. However, despite decades of research, we still don't have a definitive answer. The singularity remains one of the greatest unsolved puzzles in physics. What makes the Big Bang singularity so fascinating is that it's not just a scientific problem, it's a philosophical one too. It forces us to confront questions about the nature of existence itself. Was there truly a beginning, or is the idea of a singularity just a sign that our current theories are incomplete? Could there have been something before the Big Bang, or does time itself start at this point? These questions push the boundaries of both science and imagination, reminding us that the universe's origins are as mysterious as they are awe-inspiring. As we continue to explore the mysteries of the Big Bang singularity, we're reminded that some of the most profound questions in science remain unanswered. But every step forward brings us closer to unraveling the secrets of the universe's birth, and with it, a deeper understanding of our place in the cosmos. Now, as we step into the next chapter of the universe's story, we arrive at the end of cosmic inflation, a pivotal moment that set the stage for the hot Big Bang. Imagine the universe stretched and smoothed by inflation, suddenly hitting the brakes. This dramatic shift marks the end of the inflationary epoch, a period of rapid expansion that lasted just a fraction of a second. But what happened next is just as fascinating. As inflation came to a close, the energy that had been driving this exponential expansion didn't simply vanish. Instead, it underwent a process called reheating. Think of it like a cosmic power plant where the stored energy of inflation was converted into particles and radiation. This transformation filled the universe with the raw ingredients for everything we see today: quarks, electrons, photons, and more. It's as if the universe hit a reset button, transitioning from a cold, empty state to a hot, dense soup of matter and energy. This reheating process is crucial because it bridges the gap between inflation and the hot Big Bang. Without it, the universe would have remained a cold, lifeless expanse. Instead, reheating ignited the fireball of the early universe, setting the conditions for the formation of atoms, stars, and galaxies. It's the moment when the universe truly began to take shape, moving from a smooth, featureless state to one rich with structure and complexity. Understanding this transition is key to piecing together the universe's evolution. It explains how the seeds of cosmic structure, those tiny quantum fluctuations stretched by inflation, were able to grow into the galaxies and clusters we observe today. It also highlights the delicate balance of forces and energies that shape the cosmos, reminding us just how finely tuned the universe's early moments were. As we reflect on the end of inflation, we're reminded that even the briefest moments in cosmic history can have profound consequences. The transition from inflation to the hot Big Bang wasn't just a change in temperature or density. It was the spark that ignited the universe's incredible journey, a journey we're still unraveling today. Now, as we journey further into the universe's story, we arrive at a time when darkness gave way to light, the birth of the first stars and galaxies. Picture a universe still cooling from the fiery aftermath of the Big Bang, filled with a fog of neutral hydrogen gas. For hundreds of millions of years, this cosmic dark age persisted until something extraordinary happened. Tiny fluctuations in density, those seeds planted by cosmic inflation, began to grow. Gravity pulled matter together, forming the first clumps of gas that would ignite into the very first stars. These stars, known as population 3 stars, were unlike anything we see today. They were massive, hot, and short-lived, burning through their fuel in just a few million years. But their brief existence was transformative. As they burned, they fused hydrogen into heavier elements like carbon, oxygen, and nitrogen elements that would later become the building blocks of planets, life, and even us. When these stars died in spectacular supernova explosions, they scattered these elements across the cosmos, enriching the universe for the generations of stars and galaxies to come. But the story doesn't end there. The light from these first stars didn't just illuminate the universe, it also began to change it. This light was so intense that it ionized the surrounding hydrogen gas, stripping electrons from their atoms in a process called reionization. Over time, this reionization cleared the cosmic fog, making the universe transparent to light and setting the stage for the galaxies we see today. This era of reionization, which lasted from about 500 million to 1 billion years after the Big Bang, marks one of the most dramatic transformations in cosmic history. Today, telescopes like Hubble and James Webb are giving us an unprecedented glimpse into this ancient era. By peering deep into space, these observatories are capturing light from some of the earliest galaxies, formed just a few 100 million years after the Big Bang. The James Webb Space Telescope, in particular, is revolutionizing our understanding of this period. Its infrared vision allows it to see through dust and gas, revealing the faint glow of these primordial galaxies and helping us piece together how they formed and evolved. As we uncover more about the first stars and galaxies, we're not just learning about the distant past, we're also gaining insights into the origins of the universe's structure and the elements that make up everything around us. It's a reminder that the universe's history is written in the stars, and with each new discovery, we're reading another page of this cosmic story. Now, as we zoom out from the birth of the first stars and galaxies, we find ourselves gazing at the vast tapestry of the universe's large-scale structure. Imagine a cosmic web stretching across billions of light years, woven together by gravity and the invisible hand of dark matter. This intricate network is made up of galaxy clusters, filaments, and vast empty regions known as cosmic voids. But how did this grand design come to be? The answer lies in those tiny quantum fluctuations we've talked about earlier, the same ones that set the stage for cosmic inflation. These fluctuations, imprinted in the early universe, acted like seeds. Over billions of years, gravity amplified them, pulling matter together into dense regions that would eventually become galaxies and galaxy clusters. Meanwhile, the areas with less matter grew emptier, forming the voids we see today. But here's the twist: ordinary matter alone couldn't have done this. Enter dark matter, the mysterious substance that makes up about 85% of the universe's mass. Dark matter's gravitational pull is what truly shaped this cosmic web, guiding the formation of galaxies and clusters along its invisible threads. To understand this process, scientists rely on powerful computer simulations. These simulations recreate the universe's evolution, starting from those initial quantum fluctuations and factoring in the influence of dark matter. The results are stunningly accurate, matching what we observe in the real universe. They show how dark matter clumps together first, creating a scaffold for galaxies to form. Over time, ordinary matter, gas and dust falls into these dark matter halos, igniting the birth of stars and galaxies. But the story doesn't end there. The large-scale structure of the universe is still evolving. Galaxies continue to move along the filaments of the cosmic web, drawn together by gravity. Some collide and merge, while others drift apart, carried by the universe's expansion. This dynamic dance shapes the universe we see today and offers clues about its future. By studying this structure, we're not just mapping the cosmos, we're uncovering the fingerprints of its origins. Every galaxy cluster, every void, tells a story about the universe's past and the forces that shaped it. And as our telescopes and simulations grow more advanced, we're getting closer to understanding the full picture of this cosmic masterpiece. Now, shifting our focus to the age of the universe, we find ourselves asking one of the most profound questions in cosmology: how old is everything we see around us? The answer, as determined by modern science, is approximately 13.8 billion years. But how did scientists arrive at this precise number? The story begins with two key tools: the cosmic microwave background, or CMB, and the Hubble constant. The CMB, as we've discussed earlier, is the afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. By studying the tiny temperature fluctuations in this ancient light, scientists can trace the universe's expansion back to its earliest moments. These fluctuations act like a cosmic clock, allowing researchers to calculate how long it took for the universe to grow from its hot, dense beginnings to the vast expanse we see today. But the CMB isn't the only piece of the puzzle. The Hubble constant, named after Edwin Hubble, measures the rate at which the universe is expanding. By observing distant galaxies and measuring how fast they're moving away from us, scientists can estimate how long it's taken for the universe to reach its current size. Combining these measurements with data from the CMB provides a remarkably consistent estimate of the universe's age. What's truly astonishing is the precision of these calculations. Modern cosmology has narrowed down the universe's age to within just a few tens of millions of years, a blink of an eye on cosmic timescales. This level of accuracy is a testament to the power of human ingenuity and the tools we've developed to explore the cosmos. So, when we say the universe is 13.8 billion years old, we're not just throwing out a number. We're drawing on decades of observations, experiments, and theoretical work that have brought us closer than ever to understanding the true age of everything. And as our tools and techniques continue to improve, we may one day refine this number even further, unlocking even more secrets about the universe's origins and evolution. Now, as we peer into the distant future, we find ourselves contemplating the ultimate fate of the universe. What lies ahead for the cosmos? Scientists have proposed several possible scenarios, each shaped by the interplay of dark energy and the universe's expansion rate. Let's explore these fascinating possibilities, starting with the Big Freeze. The Big Freeze, also known as the heat death, is perhaps the most widely accepted scenario. In this model, the universe continues to expand at an accelerating rate driven by dark energy. Over trillions of years, galaxies will drift farther apart, stars will burn out, and the universe will grow colder and darker. Eventually, all that remains will be a vast, empty expanse with temperatures approaching absolute zero. It's a chilling thought, but one that aligns with our current understanding of dark energy's dominance. Next, we have the Big Crunch, a dramatic reversal of the Big Freeze. In this scenario, the expansion of the universe slows down and eventually stops, pulled back by gravity. Galaxies, stars, and even atoms would collapse into an infinitely dense point, much like the Big Bang in reverse. While this idea was once a leading contender, the discovery of dark energy and the universe's accelerating expansion has made the Big Crunch seem less likely. Still, it remains a captivating possibility, reminding us of the delicate balance between expansion and gravity. Finally, there's the Big Rip, a more extreme and violent end to the universe. Here, dark energy doesn't just accelerate the expansion, it grows stronger over time. Eventually, it would overcome all forces, tearing apart galaxies, stars, planets, and even atoms themselves. The universe would end not with a whimper but with a catastrophic rupture. While this scenario is speculative, it highlights the profound influence dark energy could have on the cosmos. Understanding these potential fates isn't just about satisfying our curiosity, it's deeply tied to cosmic inflation. The rapid expansion of the early universe set the stage for everything that followed, including the distribution of matter and the behavior of dark energy. By studying inflation, we gain insights into how the universe began and how it might end. Each scenario offers a glimpse into the delicate interplay of forces that shape our cosmic destiny. As we continue to unravel the mysteries of dark energy and cosmic inflation, we move closer to answering one of the most profound questions of all: what will become of the universe? The journey to uncover this truth is as thrilling as the possibilities themselves, reminding us that the story of the cosmos is far from over. Now shifting our focus to one of the most elusive and mysterious components of the universe, we arrive at the role of dark matter. This invisible substance makes up roughly 85% of the universe's total mass, yet it doesn't emit, absorb, or reflect light, making it nearly impossible to observe directly. So how do we know it exists? The answer lies in its gravitational effects. In the 1930s, astronomer Fritz Zwicky noticed something peculiar while studying galaxy clusters. The visible matter in these clusters wasn't enough to account for the gravitational forces holding them together. Galaxies were moving faster than they should have been if only the visible matter was pulling on them. This discrepancy led to the realization that there must be something else, something invisible, exerting a gravitational influence. That something is dark matter. Dark matter's gravitational pull doesn't just hold galaxies together, it also shapes the large-scale structure of the universe. Without it, galaxies and galaxy clusters wouldn't have formed as they did. Cosmic inflation, the rapid expansion of the early universe, set the stage for this structure by creating tiny fluctuations in density. Dark matter then acted as the scaffolding, pulling matter together to form the cosmic web we see today. In this way, dark matter is not just a passive observer, it's a key player in the universe's evolution. Despite its importance, dark matter remains one of the greatest unsolved mysteries in cosmology. Scientists have proposed various candidates for what it might be, from weakly interacting massive particles, or WIMP, to actions, hypothetical particles with extremely low mass. Detecting these particles, however, has proven to be a monumental challenge. Experiments deep underground, like those using liquid xenon detectors, aim to catch rare interactions between dark matter particles and ordinary matter. Meanwhile, space-based observatories are searching for indirect evidence, such as gamma rays produced when dark matter particles annihilate each other. The quest to understand dark matter isn't just about solving a cosmic puzzle, it's about unlocking the secrets of the universe's structure and history. By studying dark matter, we gain insights into how cosmic inflation shaped the early universe and how galaxies and galaxy clusters formed over billions of years. It's a reminder that much of the universe remains hidden from our view, waiting to be discovered. As we continue to probe the cosmos, dark matter stands as a testament to the enduring mysteries that drive our curiosity and exploration. Now turning to one of the most puzzling questions in cosmology, we encounter the Baryon asymmetry problem. This mystery revolves around a simple yet profound observation. Why is there so much more matter than antimatter in the universe? According to our current understanding of physics, matter and antimatter should have been created in equal amounts during the Big Bang. Yet, when matter and antimatter meet, they annihilate each other, leaving behind only energy. So, if equal amounts were produced, why does matter dominate the universe today? This imbalance is crucial because without it, galaxies, stars, planets, and even life as we know it wouldn't exist. Cosmic inflation and particle physics theories offer some intriguing explanations for this asymmetry. One leading idea is that during the inflationary epoch, certain conditions allowed for a slight preference for matter over antimatter. This could have been due to processes involving particles called baryons, which include protons and neutrons. Theories suggest that tiny violations of symmetry in the laws of physics, known as CP violation, might have tipped the scales in favor of matter. These violations could have occurred during the rapid expansion of the universe, creating a small but significant excess of matter. Another possibility lies in the behavior of exotic particles in the early universe. Some theories propose that heavy, unstable particles decayed unevenly, producing more matter than antimatter. These decays could have been influenced by the extreme conditions of cosmic inflation, where the universe was expanding faster than the speed of light. Over time, this slight imbalance grew as the universe cooled, leaving behind the matter-rich cosmos we observe today. The Baryon asymmetry problem isn't just a theoretical curiosity, it's a cornerstone of our existence. Without this imbalance, the universe would be filled with nothing but radiation, devoid of the structures that make life possible. Understanding how and why this asymmetry arose helps us piece together the story of the universe's origins and evolution. It also connects to broader questions about the fundamental laws of physics and whether they are truly symmetrical or if there are hidden biases at play. As scientists continue to investigate this mystery, experiments like those at the Large Hadron Collider are searching for clues in the behavior of subatomic particles. By recreating the conditions of the early universe, researchers hope to uncover the mechanisms that led to the dominance of matter. Each discovery brings us closer to solving this cosmic puzzle, reminding us that the universe is full of surprises waiting to be uncovered. With every step forward, we gain a deeper appreciation for the delicate balance that makes our existence possible. Now shifting our focus to another fascinating relic of the early universe, we encounter the cosmic neutrino background. Much like the cosmic microwave background, or CMB, this is a faint echo from the universe's infancy, but with a twist it's made up of neutrinos, some of the most elusive particles in existence. Neutrinos are incredibly lightweight, neutral particles that barely interact with matter, making them notoriously difficult to detect. Yet, their story is deeply intertwined with the Big Bang and cosmic inflation. Shortly after the Big Bang, when the universe was a seething cauldron of energy and particles, neutrinos were everywhere. They interacted freely with other particles, but as the universe expanded and cooled, they began to decouple from matter. This happened just a fraction of a second after the Big Bang, even before the CMB was formed. Once decoupled, neutrinos streamed freely through the universe, barely interacting with anything else. This cosmic neutrino background has been traveling through space ever since, carrying with it a snapshot of the universe as it was in its earliest moments. Detecting this background is no small feat. Neutrinos are so ghostly that they can pass through entire planets without a trace. However, if scientists could capture even a faint signal from the cosmic neutrino background, it would open a new window into the early universe. These neutrinos could reveal details about the conditions during cosmic inflation, the rapid expansion that shaped the universe's structure. They might also help us understand how the universe transitioned from a hot, dense state to the cooler, more structured cosmos we see today. The cosmic neutrino background could also shed light on the properties of neutrinos themselves. For instance, it might help us determine their exact masses or uncover whether they played a role in the formation of large-scale structures like galaxies and galaxy clusters. While the CMB has been a treasure trove of information, the cosmic neutrino background could complement it, offering a different perspective on the universe's origins. Efforts to detect this background are still in their early stages, but the potential rewards are immense. By studying these ancient neutrinos, we could gain new insights into the fundamental forces and particles that shaped the universe. It's a reminder that even the most elusive particles hold clues to the grand story of cosmic inflation and the Big Bang. As we continue to explore these faint whispers from the past, we move closer to unraveling the mysteries of our universe's beginnings. Now turning to a puzzle that has left cosmologists scratching their heads, we encounter the Hubble tension. This is the name given to a growing discrepancy in measurements of the universe's expansion rate, a fundamental parameter known as the Hubble constant. On one hand, we have measurements based on the cosmic microwave background, or CMB, which suggest a specific rate of expansion. On the other hand, observations of nearby galaxies and supernova point to a slightly faster rate. This inconsistency has become one of the most pressing challenges in modern cosmology, raising questions about our understanding of the universe's evolution. The Hubble tension isn't just a minor disagreement, it's a potential crack in the foundation of our cosmological models. If the universe is expanding faster than predicted by the CMB, it could mean that something is missing from our current theories. Perhaps there's an unknown ingredient in the cosmic recipe, like a new form of dark energy or an unexpected property of neutrinos. Alternatively, it might hint at flaws in our understanding of cosmic inflation, the rapid expansion that occurred just after the Big Bang. Either way, resolving this tension could lead to groundbreaking discoveries about the nature of the universe. Efforts to solve this mystery are in full swing. Scientists are using a variety of methods to refine measurements of the Hubble constant, from studying gravitational waves to observing distant quasars. Some researchers are even exploring whether the tension could be due to systematic errors in our observations, though so far, no such errors have been found. Others are considering more radical ideas, such as the possibility that dark energy evolves over time, or that our universe isn't as uniform as we once thought. What makes the Hubble tension so fascinating is its potential to reshape our understanding of cosmology. If the discrepancy is real, it could mean that our current models of the universe are incomplete, requiring new physics to explain the observed phenomena. This would be a monumental shift, akin to the discovery of dark energy in the late 1990s. On the other hand, if the tension is resolved through more precise measurements, it would reaffirm the robustness of our existing theories, including cosmic inflation. As the search for answers continues, the Hubble tension serves as a reminder of how much we still have to learn about the cosmos. It's a testament to the dynamic nature of science, where even the most well-established ideas can be challenged by new observations. Whether this tension leads to a revolution in cosmology or a deeper understanding of our current models, one thing is certain: the journey to uncover the truth will be as exciting as the discoveries themselves. Now shifting our focus to the microscopic realm, we delve into the fascinating role of quantum mechanics in the Big Bang and cosmic inflation. At the heart of this discussion is the idea that the universe's birth may have been shaped by the strange and unpredictable behavior of particles at the quantum level. Quantum mechanics, the branch of physics that governs the behavior of the smallest particles, introduces concepts that seem almost magical compared to the predictable laws of classical physics. One such concept is quantum tunneling, a phenomenon where particles can pass through barriers that would be impossible to overcome under normal circumstances. In the context of the Big Bang, quantum tunneling might explain how the universe emerged from a state of nothingness. Imagine a tiny, unstable region of space, smaller than an atom, suddenly tunneling through an energy barrier and triggering the rapid expansion we call cosmic inflation. This process, driven by quantum fluctuations, could have set the stage for the birth of the universe as we know it. These fluctuations, tiny ripples in the fabric of space-time, were stretched to enormous scales during inflation, eventually becoming the seeds for galaxies and large-scale structures. Quantum mechanics also helps us understand why the early universe was so uniform. The rapid expansion during inflation smoothed out any irregularities, but it was the quantum fluctuations that introduced the slight variations needed for structure formation. Without these quantum effects, the universe might have remained a featureless void, devoid of stars, planets, or life. The importance of quantum mechanics in the early universe cannot be overstated. It provides the framework for understanding how something as vast and complex as the cosmos could arise from the tiniest of beginnings. As we continue to explore the mysteries of the Big Bang, quantum mechanics remains a key tool in our quest to uncover the universe's deepest secrets. This interplay between the quantum world and the cosmos reminds us that even the smallest particles can have the most profound impact on the grandest scales. With this understanding of quantum mechanics in hand, we're ready to explore the next frontier, the Planck era, the earliest moment in the universe's history where the rules of quantum gravity took center stage. Now turning to the Planck era, we step into the earliest moments of the universe's existence, a time so brief and extreme that it defies our current understanding of physics. This era, named after physicist Max Planck, represents the first fraction of a second after the Big Bang, when the universe was unimaginably small, hot, and dense. Here, the forces of nature as we know them, gravity, electromagnetism, and the nuclear forces were unified into a single, all-encompassing force governed by the rules of quantum gravity. The Planck era is shrouded in mystery because it exists at the intersection of two great theories: quantum mechanics, which explains the behavior of the smallest particles, and general relativity, which describes the large-scale structure of spacetime. At this scale, the universe was so compact that quantum effects dominated, and spacetime itself may have been a seething, chaotic foam. This makes the Planck era a realm where our current laws of physics break down, leaving scientists with more questions than answers. One of the biggest challenges in studying this era is the lack of direct evidence. The extreme conditions of the Planck era left no observable traces in the universe today, making it impossible to probe with telescopes or particle accelerators. Instead, physicists rely on theoretical models and mathematical frameworks, such as string theory and loop quantum gravity, to piece together what might have happened. These theories suggest that the Planck era could hold the key to understanding the true nature of the Big Bang, including how the universe emerged from a singularity and what, if anything, existed before it. Despite the challenges, the Planck era remains a tantalizing frontier in cosmology. Unlocking its secrets could revolutionize our understanding of the universe's origins and provide insights into the fundamental nature of reality itself. As we continue to push the boundaries of science, the Planck era stands as a reminder of how much we still have to learn about the cosmos. With this glimpse into the universe's earliest moments, we're ready to explore another fascinating aspect of cosmic history: the search for exotic particles that could shed light on the Big Bang and cosmic inflation. Now shifting our focus to the cutting edge of particle physics, we delve into the search for exotic particles that could unlock the secrets of the Big Bang and cosmic inflation. At the forefront of this quest is the Large Hadron Collider, the world's most powerful particle accelerator. Nestled deep underground near Geneva, this colossal machine smashes particles together at nearly the speed of light, recreating conditions similar to those in the universe's earliest moments. One of the most intriguing theories being tested is supersymmetry, a concept that proposes every known particle has a heavier, yet-to-be-discovered counterpart. These hypothetical particles, often referred to as sparticles, could help explain why the universe is filled with matter rather than antimatter and provide clues about the nature of dark matter. If supersymmetry is proven correct, it would not only revolutionize our understanding of particle physics, but also offer insights into the forces that drove cosmic inflation. The search for exotic particles is critical because they could hold the key to understanding the universe's first moments. For instance, some theories suggest that certain particles, like the inflaton, may have triggered the rapid expansion of the universe during the inflationary epoch. Detecting such particles would provide direct evidence for cosmic inflation and help us piece together how the universe transitioned from a microscopic speck to the vast cosmos we see today. While the Large Hadron Collider has already made groundbreaking discoveries such as the Higgs boson, the hunt for exotic particles remains ongoing. Each collision in the accelerator is a window into the universe's infancy, offering scientists a chance to uncover particles that could reshape our understanding of reality. As we continue to push the boundaries of technology and theory, the search for these elusive particles reminds us that the universe's deepest mysteries are still waiting to be unraveled. With this exploration of particle physics, we're ready to turn our attention to another fascinating aspect of the early universe: the role of black holes in shaping cosmic history. Now turning to the enigmatic role of black holes in the early universe, we uncover a fascinating chapter in cosmic history. Black holes, often thought of as destructive forces, might have played a crucial part in shaping the universe during its infancy. One compelling theory suggests that primordial black holes, formed just moments after the Big Bang, could have been among the first structures to emerge in the cosmos. Unlike the black holes we observe today, which form from collapsing stars, these primordial black holes would have arisen from the extreme density fluctuations in the early universe. These ancient black holes could have been as small as an atom or as massive as a star, and their existence might hold the key to understanding cosmic inflation. Some scientists propose that these black holes could have acted as seeds for the formation of galaxies, their immense gravitational pull drawing in surrounding matter and kickstarting the growth of cosmic structures. Additionally, primordial black holes might even account for a portion of the mysterious dark matter that permeates the universe, offering a potential solution to one of cosmology's greatest puzzles. The influence of black holes on cosmic inflation is equally intriguing. During the inflationary epoch, the rapid expansion of the universe could have been influenced by the gravitational effects of these early black holes. Their presence might have created ripples in space-time, leaving imprints that we can still detect today in the cosmic microwave background. These ripples could provide clues about the conditions of the early universe and the mechanisms that drove its expansion. As we continue to explore the universe's origins, the study of primordial black holes offers a unique window into the past. By examining their potential role in cosmic inflation and galaxy formation, we gain deeper insights into the forces that shape the cosmos. This journey into the early universe reminds us that even the most mysterious phenomena, like black holes, hold the potential to illuminate the grand story of our existence. With this exploration of black holes, we now set our sights on the future of cosmology and the groundbreaking discoveries that await us. As we step into the future of cosmology, the possibilities for discovery are more exciting than ever. With cutting-edge technologies and ambitious missions on the horizon, scientists are poised to uncover even deeper secrets about the Big Bang and cosmic inflation. One of the most anticipated projects is the James Webb Space Telescope, already revolutionizing our view of the early universe. Its ability to peer back in time, capturing light from the first galaxies, is shedding new light on the cosmic dawn and the conditions that followed the Big Bang. But the James Webb Telescope is just the beginning. Upcoming missions like the European Space Agency's Euclid and NASA's Nancy Grace Roman Space Telescope aim to map the universe in unprecedented detail. These telescopes will study dark energy and dark matter, two of the most mysterious components of the cosmos, helping us understand how they influence the universe's expansion and structure. By analyzing the distribution of galaxies and the bending of light from distant objects, these missions could reveal clues about the inflationary epoch and the forces that shaped the early universe. On the ground, experiments like the Simons Observatory and the next-generation cosmic microwave background experiments are pushing the boundaries of what we know about the universe's origins. These projects will measure the CMB with extraordinary precision, searching for faint imprints of gravitational waves from cosmic inflation. If detected, these ripples in space-time would provide direct evidence for inflation, confirming one of the most profound theories in cosmology. Meanwhile, particle accelerators like the Large Hadron Collider continue to explore the fundamental building blocks of the universe. By recreating the extreme conditions of the early cosmos, scientists hope to uncover new particles or forces that could explain the Big Bang and the rapid expansion that followed. Theories like supersymmetry and string theory are being tested, offering potential insights into the quantum origins of the universe. The future of cosmology also holds promise for international collaboration. Projects like the Square Kilometre Array, a massive radio telescope being built across 2 continents, will study the universe's first stars and galaxies, as well as the cosmic web that connects them. By combining data from these diverse missions, scientists hope to piece together a more complete picture of the universe's history, from its explosive birth to its ongoing evolution. As we look ahead, the tools and technologies at our disposal are transforming our understanding of the cosmos. Each new discovery brings us closer to answering the profound questions about our origins and the nature of reality. The future of cosmology is not just about uncovering the past, it's about shaping our understanding of the universe's destiny and our place within it. With every mission, telescope, and experiment, we take another step toward unraveling the mysteries of the Big Bang and cosmic inflation, reminding us that the universe is a story still being written. Now, let's take a closer look at the cosmic microwave background, or CMB, and uncover the incredible details hidden within this ancient light. The CMB is often described as the afterglow of the Big Bang, but it's far more than just a faint glow. It's a treasure trove of information about the universe's earliest moments. One of the most fascinating aspects of the CMB is its anisotropies, tiny variations in temperature that appear as faint patches of hot and cold across the sky. These anisotropies are like fingerprints, revealing the initial conditions of the universe and offering clues about how everything we see today came to be. These temperature fluctuations might seem insignificant, but they hold the key to understanding the universe's structure. They represent the seeds of all cosmic structures, galaxies, galaxy clusters, and even the vast cosmic web that connects them. Without these tiny irregularities, the universe would be a featureless sea of matter and energy. Instead, they acted as the starting points for gravity to pull matter together, eventually forming the stars and galaxies we observe today. Recent missions like the Planck satellite have mapped these anisotropies with extraordinary precision, giving us an unprecedented view of the early universe. Planck's data revealed that the universe is remarkably uniform on large scales, but it's the subtle differences in temperature that tell the story of how complexity emerged from simplicity. These measurements also confirmed predictions made by the theory of cosmic inflation, showing that the universe expanded faster than the speed of light in its first moments, smoothing out irregularities while leaving behind the faint imprints we see in the CMB. But the CMB isn't just a snapshot of the past, it's also a window into the universe's composition. By studying the anisotropies, scientists have determined that ordinary matter, the stuff that makes up stars and planets, accounts for only about 5% of the universe's total energy. The rest is made up of dark matter and dark energy, two mysterious components that continue to puzzle researchers. The CMB's fine details have even allowed us to measure the universe's age with incredible accuracy, placing it at around 13.8 billion years old. As we continue to analyze the CMB, new discoveries are reshaping our understanding of the cosmos. For instance, anomalies in the data, such as unexpected cold spots or asymmetries, hint at phenomena that current theories can't fully explain. These mysteries drive scientists to refine their models and explore new ideas, pushing the boundaries of what we know about the universe's origins. The CMB is more than just a relic of the Big Bang. It's a roadmap to the past and a guide to the future of cosmology. With each new observation, we uncover another piece of the puzzle, bringing us closer to understanding the grand story of the universe. Now, shifting our focus to the horizon problem, we encounter one of the most puzzling mysteries of the early universe. Imagine looking at two distant regions of the cosmos that are billions of light years apart. Despite their vast separation, these regions have nearly identical temperatures, as revealed by the cosmic microwave background. But here's the catch: according to the standard Big Bang model, these regions should never have been in contact with each other. So how did they end up so perfectly synchronized? This is the essence of the horizon problem. Cosmic inflation provides an elegant solution to this conundrum. In the first fraction of a second after the Big Bang, the universe underwent an exponential expansion, growing faster than the speed of light. This rapid stretching of space brought regions that were once close together far apart, but crucially, they remained in thermal equilibrium because they had been in causal contact before inflation began. Think of it like stretching a rubber sheet with 2 points marked on it. Even as the sheet expands, the points retain their connection, preserving their shared properties. This concept of causal contact is key to understanding how inflation solves the horizon problem. Before inflation, the universe was small enough for all regions to exchange energy and reach a uniform temperature. Then, as inflation kicked in, these regions were pushed far beyond the observable horizon, yet their thermal equilibrium was preserved. This explains why the cosmic microwave background appears so remarkably uniform across the sky, even in regions that seem too distant to have ever interacted. Inflation doesn't just smooth out temperature differences, it also sets the stage for the universe's large-scale structure. The tiny quantum fluctuations present during inflation were stretched to cosmic scales, becoming the seeds for galaxies and galaxy clusters. Without inflation, the universe would lack the uniformity and structure we observe today. It's a profound idea. The same process that solved the horizon problem also laid the groundwork for the cosmos as we know it. As we delve deeper into the implications of inflation, it's clear that this theory has reshaped our understanding of the universe's origins. By addressing the horizon problem, inflation not only resolves a major cosmological puzzle, but also provides a framework for exploring other mysteries, such as the nature of dark energy and the multiverse. The more we study inflation, the more we realize how interconnected the universe's early moments were, and how they continue to influence its evolution billions of years later. Now, stepping into the realm of the multiverse, we venture into one of the most fascinating and speculative ideas in modern cosmology. The multiverse hypothesis suggests that our universe might be just one of countless others, each with its own unique set of physical laws and constants. This concept arises naturally from the theory of eternal inflation, where different regions of space stop inflating at different times, creating bubble universes that could be vastly different from our own. One type of multiverse is the inflationary multiverse, where each bubble universe forms from a separate inflationary event. These universes could have entirely different properties. Some might have stronger gravity, others might lack dark energy, and some could even have extra dimensions. Another type is the quantum multiverse, stemming from the many worlds interpretation of quantum mechanics. Here, every possible outcome of a quantum event spawns a new universe, leading to an infinite branching of realities. Then there's the mathematical multiverse, which posits that every mathematically consistent structure exists as a physical reality somewhere in the multiverse. The implications of the multiverse are profound, both for physics and philosophy. For physicists, it raises questions about the nature of reality and the limits of scientific inquiry. If other universes are forever beyond our observational reach, how can we ever test the multiverse hypothesis? This challenge has sparked debates about whether the multiverse is a scientific theory or a philosophical speculation. Yet, some researchers argue that indirect evidence, such as anomalies in the cosmic microwave background or the distribution of galaxies, could hint at the existence of other universes. Philosophically, the multiverse challenges our understanding of existence and our place in the cosmos. If countless universes exist, each with its own laws, does that make our universe less special? Or does it highlight the remarkable fine-tuning required for life to emerge in our particular corner of reality? These questions push us to rethink not only the nature of the universe but also the meaning of existence itself. Despite its allure, the multiverse hypothesis remains controversial. Critics argue that it's untestable and therefore falls outside the realm of science. Supporters, however, see it as a natural extension of our current theories, offering a way to explain the peculiarities of our universe without invoking a single, finely tuned creation event. As we continue to explore the frontiers of cosmology, the multiverse remains a tantalizing possibility, one that could forever alter our understanding of reality and our place within it. As we bring this cosmic journey to a close, let's take a moment to reflect on the 25 incredible discoveries we've explored about the Big Bang and cosmic inflation. From the cosmic microwave background, which serves as a snapshot of the universe's infancy, to the mind-bending concept of the multiverse, these breakthroughs have reshaped our understanding of reality itself. Each discovery has peeled back another layer of the cosmos, revealing a universe that is far more dynamic, mysterious, and awe-inspiring than we ever imagined. We've seen how the Hubble expansion laid the foundation for the Big Bang theory, how primordial nucleosynthesis explained the origins of the lightest elements, and how cosmic inflation solved puzzles like the flatness and horizon problems. We've delved into the role of dark energy in accelerating the universe's expansion, the search for gravitational waves from the inflationary epoch, and the tantalizing possibility of a multiverse. These discoveries haven't just answered questions, they've opened new ones, pushing the boundaries of science and philosophy alike. Yet, for all we've learned, the universe remains full of mysteries. What lies beyond the observable universe? What truly happened in the first moments of the Big Bang? Are we alone in this vast cosmos, or are there other universes out there, each with its own story to tell? These questions remind us that the journey of discovery is far from over. Every answer we find leads to new questions, and every mystery we solve reveals deeper layers of the unknown. So, as we wrap up this exploration, I leave you with this thought. The universe is not just a place we live in, it's a story we're still writing. And you, as part of this incredible journey, have the chance to be part of that story. If you've enjoyed this cosmic adventure, don't forget to subscribe and hit the notification bell so you never miss out on the latest discoveries. Together, let's keep exploring the wonders of the cosmos, one discovery at a time. Until next time, keep looking up, the universe is waiting.